Okay, yoo-hoo. We get to logarithms. So logarithmic functions. Definitely something you probably haven't encountered before. You know, it's a different kind of function. It's important to us now because it's actually the inverse of exponentials, which we'll see. That's interesting. It also has some restrictions on domain, which makes it interesting. So logarithms were invented in 1607 by a guy named John Napier. And actually my first school, the last school that I worked at, there was a student named John Napier. He didn't know that he was named the same name as a famous mathematician. But you know, the reason they invented them then at that time was because it made multiplication, made calculations easier. It did it by changing multiplication into an addition. So when is it, because we've already done this in this class, when is it that we multiply by adding? Anybody? When is it that we multiplied by adding? Say again? You have it reversed. When you multiply, you add the exponents, right? So we've actually kind of already done this. When you have the same base, like this, x to the a times x to the b, you multiply them by adding the exponents. So logarithms, in the end, are exponents. And you know, the properties of exponents end up being the properties of logarithms, and that's why this was done at the time. Because it made calculations easier. They didn't have calculators and computers and things like that. How do you think they did all this math at the time? Probably had, I just picture, you know, big monasteries full of monks sitting at tables, you know, this guy would spend his whole life doing one calculation or something. So logarithms are exponents. Now, this is an example, but realistically, when I was in high school, it was about my junior year of high school that we got our first calculators. And they were bigger than our calculators, heavier, and they did 4 things. They added and they subtracted and multiplied and divided. That was it. So when we learned logarithms, we were actually using them to do calculations, right? And the principle was this, right? And this is just a simple example just to show that it works. But if I multiply 1.2 times 1.6, I mean, I can put that in the calculator or do it by hand. That's 1.92. You know, using logarithms, what I would do is I would find the exponent that I would raise a particular base to, in this case, base 10, right here. So this is these are the logarithms, right? So when it says 1.20 is 0.0792, that means 1.2 equals 10 to the 0.0792. Okay. And then for the 1.6, the exponent, base 10, is 0.2041. So when I multiply these together, I actually just add the exponents. I get 0.2833. So then, using the tables of logarithms, I would look for where is 0.2833, and it's right there, right? So that would tell me that the answer is 1.92, right? The same answer that I got by just doing the multiplication. That's how logarithms were used to turn multiplication into addition. You know, when I was your age and we were doing this, in the back of your math book, you had tables of logarithms, pages and pages and pages of that, so that you could actually do this stuff. Now, if you consider the time, right, 1607 was, you know, it's actually in between the time when Copernicus says that the sun is the center of the universe and Galileo kind of backs him up on that. It's not that long after, I think it was like on the order of about a decade, after somebody in Holland invents the telescope. And Galileo, in Italy, close to my wife's house, was a professor at the University of Padua, and he looked through his own self-made telescope, and he saw the moons of Jupiter going around Jupiter. And he's like, if I needed any more evidence that everything doesn't go around the Earth, there you go, right? Because you can see it with the telescope. The 4 major moons of Jupiter, which are now called the Galilean moons, were going around like that. So a lot of the big, things that were done with the study of the stars and the planets happened like after logarithms, after telescopes and things like that. Now, if it was just a matter of doing calculations, we wouldn't need this anymore because we do have computers and we do have calculators, to do this. But actually, logarithmic functions are practical and are used a lot in math and science. And so we're gonna see how those functions are used. And for us, we're going to be interested in things like domains and ranges and things like that. So I think before we get started any further, I want you to have calculators on this stuff. I meant to have these out. 6. Can't you take them past back? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Thank you. Take one past back. Oh, was there an extra? Okay. And 1, 2, 3, 4, 6. Oh, you already had one. That's okay. 2, 3, 4, 5. So there will be, and there should be one extra here. Okay. So far, so good. So logarithms are related to exponentials in a way that it's one of those 3 objectives at the beginning, which are coming from the SOLs, the essential learnings, that we're supposed to know how you rearrange an exponential to make a logarithm, or how you rearrange a logarithm to make an exponential. And it's a pattern, right? And you have to just kind of memorize the pattern. But it's not terribly difficult. I mean, notice the pattern here. First of all, logarithms are written with LOG, right? LOG stands for logarithm. Okay. Then there's the base of the logarithm, which is a subscript, right? It's written just after LOG, a little bit down, maybe a little bit smaller, right? Then there's the argument of the logarithm, in this case 8, and then equals 3. Now, compare that with the exponential, which it's associated with, right? The base of the logarithm equals the base of the exponential, right? 2 and 2, right? Next one, 4 and 4. 12 and 12, 1/4 and 1/4, right? The base of the logarithm equals the base of the exponential. Okay, remember what I said at the beginning. Logarithms are exponents. So what it is that the logarithm equals is the exponent from the exponential. So since 3 was in the exponent, that's what the logarithm equals. And then what's left goes inside the logarithm. So, I mean, if you're reading this, log base 2 of 8, that's like saying, what power would I raise 2 to get 8? And the answer is 3. That's a logarithm. So let me write this down. Base of the log equals the base of the exponential. Right? And then the logarithms equal the exponents. Peter, you're taking batteries out? Don't mess with the batteries unless you don't want to use the calculator for the rest of the year. Okay. Got it? So I think I'm going to skip over that one. So try to rewrite those two as exponentials. What's the base? What's the exponent? What does it equal? What's the base of this logarithm? So what's the base of the exponential? 3, right? The base of the log equals the base of the exponential. Okay? So what is the exponent of 3? Right? Remember, the logarithm equals the exponent, so 4. And that has to equal 81. You know, when these things are like all numbers like that, you can practically just confirm it to yourself, right? 3 to the 4th is 81, sure enough. Now, to me, when I was doing this stuff and I had to go back and forth, I always was doing this. And I don't know why. I don't know whether we were taught this or what. But I'd always like go 3 to the 4th is 81. I'd start in there. 3 to the 4th is 81. Over here, I would do 7 to the 1 equals 7. At least go in that direction. Both of which seem like they're true statements. So try to rewrite those two, which are exponentials, as logarithms. You know, the truth is that the book doesn't have any problems that you convert exponentials to logarithms. They just have logarithms to exponentials. You know, we'll do a little bit of practice here, but there's no homework problems to assign that do that. I think the SOLs would expect that we probably can do both. What's the base of the exponential? What's the base of the logarithm? 14. Okay. So if you get that part right, now it's a matter of you got a 50-50 shot. What goes inside the logarithm and what goes on the other side of the equal sign? Right? What goes on the other side of the equal sign? The exponent, 0. So it's got to be log base 14 of 1 equals 0. How about the second one? What's the base? 1/2. Right? Again, what does the logarithm equal? It equals the exponent, -5, which means that the 32 goes inside, like that. Log base 1/2 of 32 equals -5. You know, try to make sure that when you write the base, you know, you write it like it doesn't just like run right into the log, like it's all written at the same level, at the same size, because it's not. It's a little bit down, a little bit smaller. I think I know what's next. So these two properties, which you actually just saw in these last couple slides, will be useful to us. We're not doing all the properties of logarithms. A lot of this stuff you'll get to if you keep going on this track. You'll get to this, and you'll spend a lot more time in logarithms than we're going to do right now. But these things, that the log of 1 always equals 0, that's a property that it'll help us when we're graphing later on, right? Or that the log base b of b equals 1. And you can convince yourself of these properties. I mean, just convert them to exponentials. What does it look like, right? Convert this one to the number 1. Convert that to an exponential. What would it be? The base would be b to the 0 equals 1. If you convert that to an exponential, that's what it looks like. B to the 0 equals 1. Well, that's a property that we had with exponents, right? Anything to the 0 equals 1. So saying log base 1 equals 0, that's like just saying anything to the 0 power is 1, just written in a different way. Okay, convert this one to an exponential. What's the base? B to the 1 equals b. Makes sense. Anything to the first power, right? B to the 1 equals b. Certainly true. So later when we're doing the graph, I like to graph a couple of points. It's useful to use these two, because otherwise you'd have to go to the calculator to figure out any table of values. You wouldn't be able to figure it out on your own. And there's about a half a dozen other properties that you'll learn somewhere down the road. Now there's 2 logarithms that are special, right? One of them is log base 10, right? And that's called a common logarithm. That's the one that I showed at the beginning of class. Common log means log base 10. And if you see just log without a base, that means it's log base 10. You don't write it. Just like if you raise something to the first power, you don't really write the 1 as an exponent. Or if you have a coefficient of 1, you don't write it anyways. Well, if you're taking the log base 10, you don't write the 10. And then another one, if you remember last time we were talking about exponential growth, and I showed you compound interest. And I showed you compound interest partly so I could introduce this number, which is E. E is is an irrational number, kind of like pi. It's about 2.7182 ... A logarithm with E as its base is called the natural logarithm, and that is abbreviated ln. That's not an I, that's an L, ln. Right? Those two you kind of need to know. Right? You have a calculator there. If you look at your calculator, right, on this side here, you see the log. That means log base 10. Because it doesn't have a base, it's log base 10. And right underneath it, you see the capital L, capital N, which you won't think is IN. That's definitely ln for natural log. So if all you have to do is like evaluate a log base 10 or an ln, there you go. Just put it in the calculator. It does it for you. Now, when you do that, let's say this log base 10, it's not like the calculator has the tables that I was referring to before inside. Like it has some finite set of tables and you just like are accessing the table when you go in there. It's actually doing a little bit of calculus inside, which is giving it an equation, which is a differential equation that it can take the input and tell you what the value is for anything that you put in. I mean, otherwise, if you had just like, let's say a fixed table in the calculator, then presumably there'd be some numbers that you would put in and say it's not in the table. But these things can do anything. So there is actually a what's called a series, which is in there, which is doing the calculation and giving you the value, so it doesn't have to, look it up in a table. So common logarithm, natural logarithm. I could imagine there being like a true-false question or something on the test about that. You need to know what those are. Now, evaluating logarithms. Okay, that's fine and dandy. You know, if you've got a log base 10 or an ln, right, log base e. But what if you got a log base 4? Or what if you got a log base 5? Right? This is how we evaluate a logarithm when it's not one of those two. So log base 4 of 64, right? These are the steps. I would go log base 4 of 64 equals x. Set it equal to x, the thing I'm trying to find out. Okay, now convert it to an exponential. What will be the exponential? What's the base of the exponential? 4. What's the exponent? X. And what does it equal? 64. So it's like saying, what power would you raise 4 to get 64? And you would say 3. 4 times 4 times 4 is 64. Now there's another thing you could do to figure it out, and this is called a change of base formula. So try this with your calculator. Put in the calculator log, just use the log button on the front of your calculator, right? Put in the log of 64 and divide it by the log of 3, or sorry, the log of 4. Right. Log 64 divided by log 4. You see where those numbers came from. And what do you get? 3. That's called a change of base formula. Okay, how about we do this log base 5 of 0.2? I mean, again, so if you use change of base formula, this one would be log of 0.2 divided by log of 5. See what you get. Okay, if I try to solve it like I did the other one, it would look like this. Log base 5 of 0.2 equals x. 5 to the x equals 0.2. Don't do this one. Sorry, my pen's stuck. Come on. Don't crap out. Oh, there we go. 0.2. 5.2 is 1/5. So what is x? -1. But again, sorry, that's a -1. If you do log of 0.2 divided by log of 5, you get it. In fact, you could use ln. You know, do ln of 0.2 divided by ln of 5. It doesn't matter what the base is. Right? ln of 0.2 divided by ln of 5 is -1. Right? So you have a way to go between different bases. Now the reality is you're not going to do any of that. Okay? The reality is that your calculator actually, this new operating system, which I just put in this one, actually has a function which will calculate logs of any bases. So this idea that we have to do change of bases for this purpose, we really don't need anymore. Here's how you can get to the log base function, which looks like log, and it lets you fill in a base and then like that. Either one of two ways. Hit the math, which is on the left side, and then either scroll down or arrow up, and you'll see right away at the bottom, it says log base. Right, so math A, and hit that, and you should see this log. So you can do it, you know, try to do log base 4 of 64. Put in the 4 there, put in the 64 there, hit enter. See if you get the 3. Okay, so you've got a log base. Did you have a question? Another way to get to it is you hit the alpha window, and then that'll bring up like 5 different functions. And that's kind of useful because some of those we end up using a bit. And you kind of want to remember that that's an easy way to get to them. Absolute value is number 1. Summation is number 2, which we'll get to and we'll use. And then the last one is log base. So either way, know where to find the log base function. So are we okay with that? Next. Okay, find the inverse of a logarithm. So remember how we found the inverse of a function? Remember, if it started with f of x, we replaced the f of x with a y. We switched the x and the y, so now it's x, y. And then we solve for y, right? So if we get to this step here, x equals log base b of y, how are we going to solve for the y? It's inside the logarithm. And the answer is, you're going to convert it to an exponential. Right? Take this thing right here and convert it to an exponential. What will be the base of the exponential? B. What will be the exponent? So what will it equal? Y. So y equals b to the x. So the inverse function is b to the x. So if you start with log base b of x as your function, then b to the x is the inverse. They're inverses of each other. Which means that when you get to solving logarithmic and exponential equations, which we're not doing, that when you want to solve a logarithmic equation, well, actually, when you want to solve a exponential equation, you take logarithms of both sides. That undoes the exponential. And in a way, you can say if you want to solve a logarithmic equation, you exponentiate both sides. But really what you do is you convert to an exponential. And it all works. Okay, so that's the important concept here. Exponentials and logarithms are inverses. That it used to be, again, before we had this log base function in the calculator to do, what we would do to graph a logarithm is we would graph the exponential, right? If I wanted to graph log base 2 of x, what I would do is I would make a table of values for 2 to the x, and then I would just switch all the x and y coordinates, and then graph them, and there was a logarithm. But it's kind of, we don't need to do that anymore because we actually can just do it directly. I can put log base 2 in the calculator. But that used to be a thing that we would do a lot. I imagine some of the other teachers probably still do it. Okay. So here's the graph of 2 to the x. Looks familiar, exponential growth. Here's the graph of log base 2 of x. Remember what we said about a graph and its inverse. It should look like they are flips across the line y equals x, and that's this red line right here. That should be like a line of symmetry, and it does look like that, right? Whereas the exponential had a y-intercept of 1, the logarithm has an x-intercept of 1. That's why log of 1 equals 0, right? Because of that point right there. Now remember, the exponential had an asymptote on the x-axis. So where do you think we're going to have an asymptote? On a logarithm. On the y-axis. And you can kind of see the way this graph is shaped that it does look like it's probably going down. Okay. Which leads us to, that is the graph of the parent function for a logarithm. Right, that's what it looks like. It has an x-intercept of 1. It has a vertical asymptote on the y-axis, which means it has an equation of x equals 0, right? It's approaching that asymptote, going down towards negative infinity, and in the first quadrant it looks like it's veering off, increasing all the time. The domain is x greater than 0, right? The values are all to the right of the middle. In fact, it does not even equal x equals 0 because it can never touch the y-axis. So remember when we did the exponential, the range was y greater than 0? Well, because this is the inverse, the domain is x greater than 0. Do you remember what was the domain of an exponential in every case? All real numbers. That's why the range of a logarithm is always all real numbers. That's not going to change. Remember, the domain of a function equals the range of the inverse. The range of the function equals the domain of the inverse. We're getting there. Now, just like I did with exponentials, where I said, if it's 2 to the x or 3 to the x, it doesn't really change much of the graph. Yeah, it changes a little, but, that's part of the formula for the parent function. It's not part of a transformation changing from a 2 to a 3. I mean, it's still the same basic shape, whether or not it's a log base 2 or log base 3. It's still the same basic shape. It still has the same asymptote, which means the same domain. It has the same intercept. It has the same range, right? Everything else is pretty much the same. The one thing a lot of what we'll get out of the last few slides here is, if all you know how to do is plug this in the calculator and then just draw me what's on your screen, believe me, you will get caught. Because you're going to end up saying things like, oh, this says a horizontal asymptote here, so it has a limited range, like it only goes up so high. That's not true. The range is all real numbers. No matter how flat that looks like it is, the range is all real numbers. There'll be some other things that we see here in this next couple of slides, which, if all you know how to do is plug it in the calculator, and even that not very well, then you'll get caught. So let's say I wanted to graph this function, log base 2 of x plus 3 plus 1. What kind of a shift in the graph is it when you add 3 inside the function? The same as we used for exponentials and absolute values. Left 3, okay? And what kind of a shift in the graph is plus 1 after the function? Up 1, okay? So understanding that the parent function of a logarithm has got an asymptote on the y-axis, right? Which one of those is going to shift the asymptote? Does going up and down shift a vertical line? No. How about going to the left 3? Yeah, I mean, if I take this whole graph and I move it left 3, that's going to move the asymptote from the y-axis to x equals negative 3. Okay, so first thing, get the asymptote in the right spot. So here's there's that, and I go back to my pen in blue. So I'm gonna label this thing. X equals negative 3. Okay, now I know this thing used to have an x-intercept of 1, but the whole graph has been shifted 3 to the left, 1, 2, 3, and up 1. So that at least that 1 point is right there. I know it. Okay. It's probably be nice to have a couple points to graph, and that's why I put those 2 properties up before. Remember the 2 properties. The one property said that the log of 1, right? Log of 1 equals 0, and the log base b of b equals 1. So if I make myself a table of values just to know a couple points, let's figure out what I plug in to x so that I make it be the log of 1. right? What would I plug in for x so that x plus 3 equals 1? Negative 2, right? So that'll be negative 2 for x. And if that means I'm taking the log of 1, which is 0. And 0 plus 1 is 1. Okay, how about for this one here? If the log base b of b equals 1, that means I would like to make this x plus 3 equal 2. Because then I would have the log base 2 of 2. So what would x be if x plus 3 equals 2? Negative 2? Negative 2 plus 3 is 1. And the log of, that's not in the logarithm. You can't add that. That's outside the logarithm. So when you put in a negative 2 here, now you're going to take the log of 1. And the log of 1 is 0. That's a property, right? 0 plus 1 is 1. Okay, now what value of x will make x plus 3 equal 2? Negative 1, right? This is arithmetic here. Negative 1. Because when I put in that, now I've got log base 2 of 2. But that's 1. By this property right here, that's 1. But I still have to add 1, and that makes 2. I mean, otherwise, in order to get the values to plug in the calculator, to graph here, I would have to use the calculator on every one. But I'm just trying to use these properties to avoid having to run to the calculator for every table of values. Okay, so these 2 points, if I graph them, look like negative 2, 1, and negative 1, 2. Now I know what the shape of the graph is, right? The shape of the graph should be something that goes like this. And these 2 points look pretty consistent there. It's going to help me draw this graph the way it should. I need to go through those points and then use that asymptote as a guide and then draw that up into the first quadrant somewhere. Okay, now try to graph that in your calculator. This is important. I want you to graph this. Right, log base 2 of x plus 3 plus 1. You can go to y equals and put it all in there. Right, that's my calculator doing it there. Are you getting something similar? Okay, that graph is wrong. Right, look at that graph. It looks like the line stops here. We know it doesn't stop. It goes on forever down. But the calculator has a hard time representing that. So if you put it in the calculator and just draw me that screen, that's just like proof. You didn't really know what you were doing. You just plugged it in the calculator and you didn't know enough to say that's not really what it looks like. So you got to be careful. That's what the calculator does with logarithms, particularly logarithms. Right? So the line does not end there. Okay, what's the domain of this function? Domain, x is greater than negative 3. Okay, what is the range? All reals. Make a big fancy R. Okay, try that one. Try to do the same thing with that one. First draw the asymptote See if you can figure out the table of values. If not, just sketch something that looks reasonable. I mean, at the very least, you should be able to move the x-intercept. So what are the shifts going on here? +1 is left, -2 is down. So I mean, again, if you're not getting this table of values that I'm doing here, at the very least, you should know that there's an x-intercept at 1 of the parent function. Just take that point, left 1, down 2, there you go. That point has to be on the graph. And you know that the basic shape and that there's an asymptote right there. Now I plotted one other point. I put in x equals 3 because if I put in x equals 3, now I've got the log base 4 of 4, which is 1. And 1 minus 2 is -1. So, right, what is the range? Or sorry, the domain. Domain is x greater than -1. The range is all real numbers. And if you graph it in the calculator, again, notice what it does to the graph. It cuts it off right there. Doesn't look like the graph. And we got to know that much about it. Because I'll have students look at that and then they'll go, the range is y greater than -2. Because they see the graph seems like it's starting there instead of saying the all real numbers. Okay, not there. One more. Let's find the error. They're trying to convert 2 to the -3 equals 1/8 into the logarithmic form. What did they do wrong? Say again. Yeah, remember the base is 2. That part was correct, but the logarithm equals the exponent, so it should have equaled -3. More than that, log base 2 of -3. Try to put it in your calculator. What do you got? Try to do log base 2 of -3. Yeah, because it's not in the domain, right? You can't take the logarithm of a negative number. It's not in the domain. Now, the interesting thing is, sometimes the calculator will give you like domain errors when you try to put something in that's not in the domain. This thing of being non-real is because there's actually imaginary solutions to this kind of thing, which I've never studied myself. I've only read about them a little bit, but the calculator obviously picks up on that. Okay, so that's everything you didn't want to know about logarithms. These are the really specific things which are about logarithms and exponentials. There's other stuff that has to do with inverses and domains and things like that, which this kind of fits into also. Okay. And the homework is that